Hi everyone, this is Mr. Lee. In this video, I'm going to go over the Modified Atwood Machine Lab that we just did. Whether you did the constant mass version or the constant force version, or maybe you did both, it's important to know the end result for both versions of the lab. So let's begin. The first thing I want to do is I want to go over the constant mass version. Okay, so before we dive right in, let's start off with a quick little drawing of the situation. So we had the ramp right there, we had the pulley, and we had the cart, and the cart had a string attached, and on the string was another hanging mass like so. Okay, and I believe that on your cart you had different masses, which I will just identify as these red lines. Okay, so we had multiple masses on the cart and we had a hanging mass here. And the whole idea here was that we were uh, investigating the idea of constant mass. So let's first identify a couple of things. Put a little star here. The idea of the mass of the system, or whatever we call the system. So in the previous unit, we were looking at systems, we just never really called it that. So whenever we made a interaction diagram, our interaction diagram was essentially what we call the system. But now I'm just introducing a different vocabulary term for you. So in this lab here, if I were to look at the system, and if I were to draw like a dotted line around the system here, and I were to ask you, okay, what are all the things within this dotted line, within this dotted circle that we are, I guess, investigating? And we would say, okay, so we have the cart, we have the objects on the cart, right? And we even have the hanging object, right? And for the sake of this lab, we said that we had to pretend that this string was massless. And so we're not going to include that in the system here because we want to look at the mass of the system. And yeah, and that will be it, right? And so if we're looking for the mass of the system, okay, we just had to look at all the objects within the system. All right. Now, if we're looking at all the things that were interacting with the system. Okay, so these are all the things that we will put on a interaction diagram, right? We will say, okay, so we have the surface, okay, and for the surface, we will call that the F of n, or the normal force. We would have the string, which we will call the force of the tension, and we would, of course, have the earth. And in this case, it will be the force of gravity, but let's put a little star here. The only force of gravity, or the weight that is actually affecting the system or interacting with the system, will be the hanging objects weight, right? Because the weight of the cart isn't affecting how this object is accelerating. Okay, so that's our system. It's really helpful if you were to, like, when you're defining a system, to draw a circle around what you're calling or what you're looking at, for the sake of I guess the problem, and when we're solving things numerically. Okay, so let's go into the lab itself. In order to do this lab's investigation, we had to use a old equation from Unit 2, and we'll be using this a lot more. So this is delta x is equal to v initial t plus 1/2 at squared. Okay, we'll be using that one a lot, by the way. And we said that the initial velocity, because it's at rest, that'll be 0. And if we were to mathematically find acceleration, oh, by the way, I think everyone should have released it so that it travels a 1/2 of a meter. So we will get a 1/2 of the meter is equal to 1/2 at squared. And then multiply 2 to both sides, we will get 1 at squared. And so our formula becomes, our acceleration is 1 over t squared. And this is if and only if our delta x was truly 0.5 meters. Okay, so the formula that you will be using throughout this course is the first one. Okay, but we turned that initial equation to something a little bit more digestible based on the physical situation, okay, that we're working with. All right, Now, for this lab, what we had to do is, because we had to have constant mass for the system, we had to remove a mass from the cart. If you just saw what I just did, I erased one of the red lines and added to the hanging mass, okay? And then we would get data, right? And then we would repeat. We would remove a mass from the cart, add it to the hanging mass. And then we kept on doing this, okay, so that we would have our data. So the mass of the system remained constant, and that is key for this. So even though the mass of the system remained constant, it's important to know that the interacting force, okay, which is the weight of the hanging object. So let's put that there. So I'm going to highlight this because this is key. This was changing. Okay, that was changing, and that is how we came up with our axes for our graph. We had a acceleration force graph, and hopefully our data, if I were to do a quick little sketch, had a linear line that looked something like this. Of course, our units are meters per second squared, and our units for force is just newtons. So this slope, if you look here, if I were to ask you, okay, describe the slope, you would say, well, Mr. Lee, the slope is constant, right? As a constant value. It's not curved. And this is important. Because we are using this vocabulary of the slope being constant, you have to ask yourself, all right, so what does this slope mean? So what does the slope mean? And based on what your value was for this slope, hopefully the groups that did this had an aha kind of moment with the value of the slope. But for those of you that didn't do this lab, the whole point of this lab was that we were investigating what constant mass was. And so if your slope was constant, that must mean that the slope for this graph represented the total mass of the system. Okay? System. All right, now I'm going to introduce to you some terminology here. In order to show this relationship, we're going to write it as acceleration is directly proportional to the force. And let's put a little highlighted there because that is important, and we will come back to that. All right, so that was part one of the lab, and part two, for those of you that did this one, we had to do a constant force. All right, so if we were to do a quick little sketch of the situation, we had a cart there, and we had the pulley, right, and we had the object that was hanging down, okay, and I believe we had different masses attached to the cart. And so the system is the same. We're looking at the system here, but what we're doing is only the interacting, okay, force is constant. And for us, the only interacting force, and make sure you can identify this, would be the force of gravity on this hanging mass. So we didn't change that at all. So instead what we did is we removed mass from cart. All right, so that's a changing variable. We were decreasing the number of mass or increasing based on how you actually did the lab. All right, so when you got your data, you also timed it, and we used the same formula. Delta x is equal to 1/2 at squared plus v initial t. Once again, I implore you, either keep this to memory or just have this readily available for you, because we'll be using this formula a lot. And we found that the acceleration is still 1/t squared, okay, because they also had a same distance of 0.5 meters, and our initial velocity was still 0 meters per second, okay? And so from there, they were able to plot the following. They were able to plot acceleration versus mass. And the data that they got was very unique. We never saw data like this. Let's do a quick sketch of the data. Okay, so here, this is a hyperbole. The data they got gave them something that looks like this. And so we had to do something that we didn't do for a long time. We had to linearize. Okay, because for science, we always want to look at data as if it were a a linear trend because that just makes describing it a lot easier. And so hopefully they went to that worksheet that I gave them at the beginning of the year, and they found in order to linearize this shape, you had to make your x-axis, which is your mass, 1 over m. So they had to go to their data table and do 1 over m. And then when they replotted that data, they got a linear line like this. So this is important here because this is the slope, and the slope for this is constant. And once again, I'm asking you, what was constant in this situation? And the answer would be, it would be the force, right? It was a constant unbalanced force. And so because this force was a constant force, we can say that the slope for this graph here represents the force, aka the weight of the hanging object. All right, and that is for this lab. All right, and with this, we can come up with a relationship where it is A is directly proportional to 1 over m, right? Yeah, and a couple of important things. The units for the slope, because it's force, the units for this would be newtons. Okay, now I'm going to highlight this as well, because for the next section, I want us to be able to come up with the general math equation that we can use for this unit. This is a formula that we came up with in the previous unit, but now we'll be using this formula all the time, so it's going to be good to have. So the two relationships that we found was that acceleration is directly proportional to force, and acceleration is directly proportional to 1 over the mass. And so what we can do is we can combine these into one relationship. We can say acceleration is directly proportional to the force, and is directly proportional to 1 over the mass. Okay? And so this is the big relationship for this unit. Now it's this relationship here is what we call Newton's second law, which states that if you have an unbalanced, okay, so this word unbalanced, you might read it as net or total, okay, if you have an unbalanced force on an object or system, okay, by the way, the object/system, that is the M in the formula, the system will accelerate, and that is just the A. Okay, so if you have an unbalanced force on a object or a system, the system or object will accelerate. So I'm going to highlight all the parts that is in the formula. We have F, we have M, and we have A. And from there, we come up with a formula, F equals ma. But this word net here, we will use this Greek symbol sigma. This just means the total. Okay, so the total force is equal to the system, which is m, and how that system is accelerating. Now, we were using this formula in the previous unit, but keep in mind that in the previous unit, all of our forces were balanced. Okay, so if you have a balanced system, or sometimes you might see the word equilibrium, that means your acceleration is 0 meters per second squared, and that means that your net force, okay, all the forces, when we added them up, had to equal to 0 newtons. But if we are unbalanced, okay, now the system will accelerate. So there's a couple of things that I want to just point out before we end this video, okay? This F here, this is all about the interaction diagrams that we practiced in the previous unit, okay? That's how we get all the forces. So using free body diagrams or force body diagrams, coming up with the interaction diagrams, okay? And this acceleration, okay, let's do this in a different color. This is acceleration was all about units 1 and 2. This was, well, mainly unit 2. And from unit 2, we had to use 3 new formulas. And so I'm going to take the time right now to write those 3 formulas down. We had delta x, which is equal to v initial times t plus 1/2 AT squared, which is the formula that we used. We have VF is equal to V initial plus A times T, and VF final squared is equal to V initial squared plus 2 times the acceleration times delta x. Okay, these are the three accelerated motion formulas. We can only use these if our objects are accelerating. Okay, and from there, we also, from Unit 2 and Unit 1, we came up with two new type of graphs. We had a position time graph and a velocity time graph. Okay, and so for here, if you remember, the position time graphs, our slopes were curved. Okay, and for here, the velocity time graph, the big idea here was that our slopes equal the acceleration. All right, and we'll see a lot more of those, but it's important to know that everything that we did in the past is still present, and we are still practicing everything from units 1, 2, 3, and now we're just combining them all into one giant unit. All right, so once again, this lab, very important. We will, I guess I would say that most of the problems that we do is based off of this lab. And so make sure you have a good foundational knowledge of what happened, and I'll see you next time. Bye-bye.